So let's start with Chapter 6, which, starting where we're leaving off with the simulations, talking about potential sweeps, or potential sweep methods. And the idea here is just, rather than doing potential steps, which you're limited to a particular potential when you do the step, let's continuously vary the potential with time and monitor the current that way. And as we'll see, that actually adds a lot of value to our experiment. We can actually see a lot of additional information in one experiment that would otherwise take many experiments doing potential steps. First of all, let's see why we might want to do potential sweeps. Let's think about an experiment in which we really wanted to understand a reaction, an electrochemical reaction. It may be a complicated one. So what we might want to do is look at all possible current, time, and potential points. In other words, in a three-dimensional surface, if we looked at the current as a function of potential and time, we would have a pretty accurate representation of the system. And by looking at that surface, we could actually model the exact process going on, in principle anyway. So if we did that, let's suppose we did that. Well, we can make a plot here where we might have time on this axis and potential on this axis. And so if we step to say from a positive to a negative potential, we would get the Cottrell type current versus potential region. Whereas if we step to very low potentials, we get basically zero current. And so we would see a set of waves that may look something like so. I'm not drawing this exactly correctly, but you can see the idea. And if we compare, for example, a line along one particular time, maybe I use a different color. If we take a cut along one particular time, this would be like our sampled current voltammetry, and we would get an I versus E curve like so, as we'd expect. So this would be a constant time. If we did alternately a cut along here at a constant potential, that would be just like a normal reversible Cottrell, or not a Cottrell step, but a reversible potential step, or just a potential step. And so if it's reversible, we would get this exponential type decay, as we'd expect. What if we took a cut along this direction, though? In this case, we're going to vary both time and potential simultaneously, and we can monitor the current like that way. What advantage would that have? Well, we wouldn't get all the information that we would get by doing all these experiments, but we could, by varying the time it took to do a cut along there, we could actually get a pretty accurate idea. We wouldn't have all these perhaps redundant data points in our model. We can look at a few of them at the same time. So I actually had a couple things in the notes that show you that. Here would be a plot of the sampled Nernstian current as a function of potential time. Now this is a Nernstian situation, so this would be a reversible potential steps. Now if it's not Nernstian, then it would have a different shape. But you can see along this axis we have time from short to long times, and here's potential from positive potentials to negative potentials. So this would be like steps from a very low or very positive potential where no reaction is occurring to a more negative potential where we have a reduction occurring. And here you can see if we concentrate only on a short time and we cut along this, you can see the shape of a sigmoid as we'd expect for a sampled current voltammogram. And if you look along pretty much any time, you'd see what that sigmoidal shape would be like. And here, even at long times, you see that sigmoidal shape is reflected. Again, as we expect, as we make time shorter, that current increases as you like. On the other hand, if we cut along this dimension, you see our IT curves with the exponential decay, or t to the minus 1/2 decay, until we get to potentials where there's really no reaction occurring, and then we don't see that decay anymore. What we're really interested in is, say, let's look along a cut. Let's go from, say, 0 to 6 seconds, this cut along this direction, or maybe 0 to 20 seconds along this direction. So this would take a longer amount of time to go that 0.6 volts than it does to go in this, for this particular case. What do we get? Well, these are those cuts across that IET surface. Here with the circles are the 0 to 6 volt thing. That's the faster cut. And you can see the current is larger, and it decays as we get past about 0.1 volt. 0 to 20 seconds, we see a cut like that. And so we see these shapes with a peak and a decay that are characteristic for those cuts along that axis. Now, these are not exactly the same as shapes as we'd get if we do potential sweeps. We'll see that in a second. But they capture kind of the essence of the potential sweeps that we'll see about. So rather than doing a cut across the surface, we're actually just doing a direct scan, and that means the conditions are slightly different during the scan. But will see an increase, a peak, and then a drop-off later on. So now, in our experiments, we're not going to do cuts like that. We're not going to make the whole plot and then do cuts across it. That would be a waste of time. We wouldn't need to do sweeps if we could make the whole current IET surface. We'll just do sweeps. And so we want to calculate the current that we see when we do sweeps across at various potentials and times. So the basic experiment is we have a potential and a time, and we're going to sweep in a linear fashion. Now, all the stuff we're talking about are going to be linear sweeps. It doesn't have to be linear. In fact, there's some recent work where we do sinusoidal type sweeps, and you get some advantages, some disadvantages, but the theory is quite a bit easier with linear sweeps. It's not very easy even as it is. So anyway, the potential as a function of time is equal to our initial potential minus VT, which we've just said. So the slope here, again, the scan rate is V. And so V is typically in volts per second, sometimes millivolts per second. If you look in the old literature, sometimes it's volts per minute or millivolts per minute. But now it's pretty much standard volts per second. T is in seconds all the time. Now, what do we see? Well, it turns out for a Nernstian type graph, a Nernstian type response, we see a curve something like this. At some potential before reaction really can occur, we don't really see much current. Then we see an exponential increase, which decays. So it doesn't rise quite as fast until we get to a peak, and then a decay, like that. So this initial rise is an exponential, and that's what you'd expect, because that's a kinetic type thing. Remember, the current is going to increase as an exponential function of potential. As we get to a mass transport limited region, which is in here, the current drops off. And then, just like in the Cottrell case, we get, as we go here, the concentration at the electrode interface is 0, so we get a t to the minus 1/2 decay for our linear sweep voltammogram. Otherwise known as the LSV. And again, this is the reversible case. It looked slightly differently for other types of kinetics. This actually is not used very much anymore. It's just as easy to do a variant of the linear sweep. It's called the cyclic voltammogram, or cyclic sometimes people say, where you start here and you sweep out to some point just like before, but then you sweep perhaps back to the initials, perhaps to some other point. But the point would be you'd have an E initial. There would be this special potential where we switch going from a positive slope or a negative slope of change of potential to the opposite slope. And almost always this V is equal to the V on the other side. So we hardly ever change the sweep rate when we change the direction of the sweep. And so this time would be actually a special time, they call it lambda. And so that's E lambda there. So what do we see for current? Well, if we plotted the current versus time, we would see this same curve as before with the decay. And then it turns out we'll see a curve that looks something like this, and we'll explain the shape of that curve a little bit later. It's not that critical right now. But something like that, if we plot current versus time. Turns out that it's really more useful and it's more informative to plot current versus potential, because that's really what we're interested in. We want current potential curves. So if we plot current versus potential, we see a curve that looks initially like this, because this is what we'd expect, and then on the reverse looks like that. And so we get these funny duck-shaped looking curves. And it turns out because they're so funny, they're not very symmetric. It turns out your eye can actually pick out a lot of changes from the basic shape without actually having to do the calculations. Rather than these Cottrell curves, which pretty much look all the same until you actually sit down and do all the numbers and figure out what's going on. And these particular shapes are for, I'll call them for Nernstian and, particularly important, planar diffusion. In other words, we're talking about linear type diffusion to large planar electrodes, and that's the shape that we see. When we don't have planar diffusion, the shape actually looks quite different. These don't look at all like the current potential curves we see up here, for example, like we saw before. Why is that? Well, we have not included the effective mass transport in the same way as we see here. It turns out because of the mass transport effects, we see quite a bit different shape for these cyclic voltammograms than we saw previously. And so this is what you really would see if you swept out and back out doing the cyclic voltammogram. Now the book has the theory, and I'm not going to go through the theory, which you're probably going to thank me for, because some of it is pretty straightforward. Some of it is kind of hairy. One of the problems with the cyclic voltammograms, as we discussed with that paper last week, is that it's really not amenable. Even the reversible case, you can't actually solve exactly using the Laplace transform method. You can get it into the Laplace plane, but you can't get it out. So you can't invert the calculation. So you have to do a numerical method to get the solution. So it turns out that most people now use digital simulations to do the calculations, even for the reversible case. But that paper by Nicholson and Shane does show you how to do that analytically, or with analytical and numerical methods. Okay. Well, let's first of all look at what happens when we do a reversible, when we have reversible kinetics. At a planar electrode. And these are all going to be diffusional-based planar electrode results. We'll talk about what happens differently later. Again, the potential E versus time is equal to the initial potential, and these are LSV results. Let's talk about LSV results first. E initial minus VT. Now, because it's Nernstian, the concentration of O and R at the electrode surface is set by the Nernst equation, and we have the potential. So all we have to do then to get the concentration trying to think why I have R there. No. Concentration of O and concentration of R are at the electrode interface is equal to the Nernst equation result. Now, this particular case, this function of time can, like I said, can be Laplace, but it's not a constant. So since it's a function of time, we have to take it into the Laplace plane, and so getting it out in is not so bad, but getting it out is the problem. So again, numerical solutions are required even in this case. And as we saw last week, that's the standard paper sort of people always refer to. They did that, and you saw the result. There was a table of numbers, and they said the current was for, in this case, again, with CO star not equal to 0, and CR star approximately equal to 0. The result is like so. Where we have this part here, they call a current function. And sigma t is equal to NF VT over RT. Okay, and since it's VT is just a potential, we can just write it as a potential. And the chi sigma t is the result, is the function of sigma t, and that's in tabular form. So there's no formula that gives us this chi sigma t. It actually just has to be calculated and presented as a table of numbers. It's a function of sigma t, which you have to calculate and then put into the value and get the number out, or which I think you've done for your problem sets. And it said Nicholson and Shane, you've got that paper. As you saw, the maximum peak current is equal to 0.4463 NFA C0 star NF over RT. V to the 1/2, D0 to the 1/2. Let's look at that a little bit carefully. We see the maximum current is this constant, which is just a result of collecting some numbers together and the fact that it's a tabulated number. It's proportional to the area, as you might expect, for a planar diffusion, the concentration. It's also proportional to this NF over RT to the 1/2 power, which is kind of unusual. What's interesting is the peak current increases as the scan rate increases. And that's kind of what you'd expect from that little plot I showed you. This is a faster scan rate than this one, essentially, for that cut. And so the peak current does increase, and it increases as the square root of the scan rate rather than as the scan rate increases. So that's interesting. So we go up by a factor of 10 in scan rate. Peak current's going to go up by a factor of 3 point something. And it's also proportional to the square root of the diffusion coefficient. IP max that's the value of it. It's also found at a particular value of potential, and it's equal to EP minus E1 half times N equal to minus 28.5 millivolts. And that actually is at 25 degrees C. Or EP is the peak current potential. So this would be EP. And the value in units in a simpler form of the function, still not very simple. This is the one that's in the back here, it's in the front of your book actually, is this particular form of the equation, which is the one I remember, try to remember. Sometimes people call that the sand equation. This particular form of the equation holds at 25 degrees C. The concentration in moles per cubic centimeter, D in moles or in centimeters squared per second, and A in square centimeters. So this is just a collection of constants. Again, notice the peak current is dependent on the square root of the scan rate. It's also interestingly dependent on the 3/2 power to the number of electrons. So rather than the peak current increasing by 2 when we go to a 2-electron process, it increases by the square root, 3/2 the value of that. E1 half, oops, is generally equal to the E0, but it also depends a little bit on the asymmetry that is present in the different diffusion coefficients. So this again, remember this part here is equal to that squiggly E part. And so as the ratio of R to O diffusion coefficient changes, we'll see a slight change in the E1 half value away from the standard potential. So if we look at a linear sweep voltammogram, what we're going to see? We're going to see a plot like this. Where the maximum peak current is 0.4463 when we use this so-called current function. And EP here, E1 half is not the half peak potential, but it's somewhere in between the half peak potential. And in fact, there is a half peak potential here, which the abbreviated EP divided by 2. The reason sometimes people are interested in the half peak potential is that it turns out that the peak here is pretty broad and it's not ill-defined, but it's broad enough so that there's quite a bit of error in associating an actual value for the peak potential. It might be off by 2 millivolts or more. And it's sometimes easier and more exact to look at the EP over 2 value, because what you can, since that's a sharper curve, it's actually more, it's easier to get that EP over 2 value more accurately. EP over 2 should be equal to the E1 half value plus 28 over N millivolts at 25 degrees C. Now notice there's always reference to a particular temperature. As the temperature changes, the potential scale actually increases or decreases. As you go to higher temperatures, the temperature scale actually the potential scale contracts, and so these numbers get smaller. You go to longer temperatures, the potential scale expands. And so this can be very something to catch the novice is to, if they do an experiment at low temperatures, they might see large peak separations and say, well, that's not a reversible system. Well, in fact, it's just a temperature effect, and it still can be reversible even at low temperatures or so on. So this value is, for example, I'm sorry, I said contracts, so that expands at high temperatures. 35 millivolts at 100 degrees C and 25.65 at 0 degrees C. So you can see how much those change. It's not insignificant amounts. All right. So peak current is proportional to the concentration, the number of electrons to the 3/2 power, and the diffusion coefficient to the 1/2 power, and the square root of the scan rate. So not necessarily all most convenient things to be proportional to, but typically for a particular experiment you know the concentration, you can find you set the scan rate, and so you're usually not so clear about what the number of electrons are and what the diffusion coefficient is. And so those are either, well, the number of electrons is usually 0 or 1 or 2 or 3 or something like that. So that's easier to figure out typically. These linear sweep results are not usually as accurate as the Cottrell experiments for determining things like diffusion coefficients. So if I was going to determine diffusion coefficients, I would not necessarily use the linear sweep voltammograms. I think a Cottrell experiment would be much more accurate at doing the same thing. Why is that? Well, it turns out that this assumes a reversible behavior, which is not a very good assumption. Most cyclic voltammograms can be made reversible if you go slow enough, but remember, if you go really slow, you start to have to worry about spherical effects and convection and so on. So it's hard to go sometimes sufficiently slow to make them reversible. And so if you don't go slow, you can have a kinetic effect. Also, you can have an important bad effect, which is called an IR drop. And we've talked about IR drop before. Remember, IR drop is a potential that develops that's associated with the flow of current through the solution resistance. And so if we have a solution resistance, we will now, when we force the current through it, cause the potential that we think we're applying to be different by a factor of IRU. Since the current is not a linear function, you see here it's not a linear function, the IR drop isn't just a linear change in the potential, it's actually a complicated change. And so with cyclic or linear sweep voltammograms or cyclic voltammograms, the effect of IR drop is very disagreeable. So instead of getting a reversible curve like that, you might get a curve that looks like that. And the problem with that curve is that this curve with IR drop actually looks a lot like a curve that might be seen with heterogeneous kinetics. So it's easy to associate slow rate constants with the effect of maybe just an IR drop. Notice the peak has shifted. The peak current has dropped. And so both of those effects are not what you want to see if you're trying to make accurate measurements. So you usually have to try to particularly minimize the effect of IR drop by using low amounts of current, by using smaller electrodes, or minimize the effect of resistance by using more conductive solutions, or by using electronic means of correction in your potentiostat, which we'll talk about later. Now chronoamps, on the other hand, or chronoamperometry, is much less sensitive. It will still have IR drop, but since you're stepping out to this plateau, if the plateau region is shifted to here because of the IR drop, it's no big deal. You're still on the plateau. So IR drop can be largely eliminated as a possibility with chronoamperometry experiments. So that's why you might prefer to use a potential step experiment to do these calculations rather than CV. The other problem with voltammograms like this is the capacitance effect. remember, for a scan rate linear sweep of potential, we calculated or we showed the equation anyway for the charging current that we see for applying a potential to a capacitor, and you saw that it's equal to VCD. And so for our electrode, because it has a double layer capacitance to it, when we're applying this sweep rate, we will see a current, this I sub C, flowing when we're doing the experiment. And the faster we sweep, the more current that flows. Notice that the current is proportional to the scan rate, whereas the Faradaic current, the current up here, is proportional to the scan rate to the 1/2 power. So as we sweep faster and faster, proportionately more of the current that we observe is going to be due to this charging current, which is also not so great. So when we see charging current, we might see a curve like this, where here's the normal wave, and on top of that wave we have this charging current, or underneath that wave we have the charging current. If we sweep faster, charging current is 10 times more. And so our curve might look like that. And that's sometimes unacceptable. Pretty much all the time it's unacceptable. So not really much you can do to get around that. That's the fundamental thing. You can use smaller electrodes because the capacitance is proportional to the area of the electrode. So you go to smaller electrodes, you can remove that effect. How's the tape holding out?
It's doing good.
All right.
45
45
minutes.
minutes?
Yeah, put in another time.
Oh, okay. Let's do a couple more things. Again, we've not done the calculations. We've just written down the results. But I think we have a pretty good idea how to do the calculations. So if you need to, you can go and do those. Totally irreversible systems. Remember, these are just like totally irreversible systems we saw before. The idea here is that we have an electrode reaction where we say reduce A. The forward rate of electron transfer is the only electron transfer rate that we consider. We don't ever consider a back rate of electron transfer. And in those cases, we saw those with potential steps. For current sweeps, peak current is 2.99 times 10 to the 5 n alpha n sub A to the 1/2 power, A C0 star D to the 1/2, and V to the 1/2. And this alpha n sub A, just like before, is the E in the rate determining step. So the peak current is actually it's a little smaller than the peak current in the reversible case. But depending a little bit on what the alpha n sub A value is, usually it's 0.5, so that's why it's smaller. And but the peak current is the same, no matter what, really. So we don't see a shift in the peak current value. It doesn't change with kinetics. It does change with scan rate, just like before, to the V to the 1/2 power. Changes with the area and the concentration of the diffusion coefficient. What does happen with the totally irreversible case is the peak position, E peak, shifts negative by 30 alpha n sub A millivolts at 25 degrees C for a decade change in the scan rate. So as we increase the scan rate, the peak shifts out farther and farther and farther. And the reason for that is that since it's irreversible, it has a kinetic term associated with it. By making the scan rate faster, we're essentially decreasing the time for the reaction to occur. So we have to have more potential to overcome that kinetic barrier. And so that's why it's shifting out with time. So IP is proportional to the square root of the scan rate and concentration. Now the intermediate case is the quasi-reversible system. Here the current is proportional to the square root of the scan rate, but it's not proportional necessarily to the concentration, because depending on what the kinetic value is, it won't be directly proportional to the concentration. What happens is that we have to consider clearly what the shape of what the value of the kinetic terms are. So the shape of the peak and the position depends on K0 and alpha. And K0 is usually formulated into a dimensionless form, and lambda is often the letter that people use to refer to dimensionless rate constant. Lambda, it would be equal to, in some formula, it depends a little bit. Sometimes there's a pi in here, and sometimes there's not a pi, depending on what people are using. So make sure you check that if you're using a formula, it's the same formula as you expect. It would be, lambda would be d0 to the 1 minus alpha power, d sub r to the alpha power, so as lambda becomes large, we can think that either the K0 has increased, in other words, the rate has become faster, or we've dropped the scan rate down. So either way is appropriate. We can think about the scan rate being made smaller. That means that even with slower values or smaller values of the K0, the lambda can still be large. So by increasing the rate constant, we can make lambda larger. Usually our knob that we can turn to adjust the lambda is the scan rate. So by turning the knob, we can make lambda large or small by scanning larger, faster, or slower rates. And so often we can turn the knob enough to make lambda be essentially a reversible case, and sometimes we can turn the knob enough so that lambda can be essentially an irreversible case. And if we're lucky, we can shift the whole current potential curve from reversible, quasi-reversible to irreversible, and that often gives us very good information about the rate constant and kinetics. Unlike the case for the irreversible and the reversible case, the peak position and shape, as I said, changes with the scan rate. For large values of lambda, the curve would be identical to the reversible case. As we make lambda smaller, the peak shifts just like the irreversible case, and the peak current drops somewhat like that. I suppose lambda is about 0.1 in that case. And just like before, if we change alpha from 0.5, we see changes in the shape of the wave. And so if we make alpha 0.7, for example, peak current is going to be a little bit more steep. Alpha 0.3, peak current is going to be less steep. And so by looking at the shape of the wave, sometimes we can tell what the alpha value is. Again, we can't use the shape, we can't get the concentration out of these peaks because of that shift around with with scan rate. So even small changes in the scan rate change the shape and the position of the wave. Unlike the irreversible case where the peak current always were proportional to the K0 or the C0. Okay, one last thing and then we'll quit here. If we look at a function of EP over EP2, or the half peak potential, times NF over RT, as a function of the logarithm of lambda, what we see is curves that look something like this. In fact, the book has better pictures of these. And these all have to be calculated by simulated voltammograms or so on to get the shapes of these. And what you're seeing here, as these curves take off, what we're seeing is a shift in the peak. That's basically how broad that peak is and so on. And what you see is that as lambda becomes small, that shift now becomes a linear function of log of lambda. And that's the case for irreversible kinetics. When lambda is large, we don't see any shift, and that's the reversible kinetic effect. Only in this region here are we talking about the quasi-reversible case, and you can see why we have some trouble, because it's a nonlinear change in, say, the peak position and so on. That's what we're talking about. What's the difference between the reversible and quasi-reversible? Some general rules. If lambda is greater than 15, that's a reversible situation. Quasi-reversible would be lambda would be between 15 and 10 to the minus 2 times 1 minus alpha. That's a quasi-reversible case. Anytime lambda is less than about 10 to the minus 2 times 1 minus alpha, we're talking about irreversible. Those aren't hard and fast numbers, but they're numbers that you can think about asking yourself: quasi-reversible, irreversible, or reversible.
Is 1 minus alpha or 1 plus alpha?
1 plus alpha here. And you can actually, and you see there's a, for reversible, that would be if we had a particular temperature, at room temperature, K0 would have to be about 0.3 times the square root of the scan rate. So let's suppose we're doing 1 volt per second. K0 would have to be greater than 0.3 centimeters per second. And so that's a good example of why K0, 0.3 and larger would be considered fast, because 1 volt per second would be a typical scan rate, maybe even faster than typical. And so anything bigger than 0.3 would be reversible under those conditions. Of course, we can do faster scan rates. We could go up to 1,000 or even 100,000 or 1,000,000 volts per second under certain conditions. In that case, K0 would have to be quite a bit faster than that 0.3 value to be reversible under those time scales. All right. Well, I've gone through that kind of fast. So next time what we'll do is we'll look at some simulations on the computer. And in fact, they are already there. So if you want to look at them already by yourself, you can look at them. And we'll see how the shapes of the curves changes under these conditions and so on. We'll talk a little bit about cyclic voltammograms, which are the reverse sweep and so on. And that, again, is a little bit more useful for most cases because we get a little bit more information out of the experiment. We'll do that next time. Of course, next time is not next week. It's the week after next week. All right. We'll take a little break.